Well, I think that the title of my talk says nothing for non-specialists in the field of logic of random structures, but I have a very detailed introduction, and it is most part of my talk, and I will explain everything about this conjecture. Okay, so let me start from the main definitions, and I'm going to speak about formal languages and how we can represent properties of graph. So let me start from some simple examples. Let me consider the property of containing a triangle, and it can be expressed in this way, and such a way of expressing properties is called first-order language. So how can we construct properties using first-order language? We can do it using these symbols, relational symbols, so these two symbols. The first one is for the adjacency, and the second one is for equality. Logical connectivities, variables which express vertices of graph, and quantifiers. And I will denote a set of all such finite sentences in this way. And when I want to say that a sentence is true for the graph, then I will write it in this way. So it is a common way of writing such things in the model theory. One definition for such sentences that I want to explain is variable width, or the number of different variables of a sentence. So what does it mean? So simply it means the number of different variables. So in the sentence you have different variables, you count the number, and this is it. But it seems like you can count the quantifiers, and the number of quantifiers will be the same. It is not exactly so, because, for example, you can say there exists something and there exists something, and you can use the same variable x inside. But you can also use, in a sequence of nested quantifiers, you also can use the same variable as in this example. So here we have exists x, and here we have also exists x, and the sequence exists, and exists is nested. To explain how we can do it, I want to show you this example and to explain what property it represents. So what do we have? There exists x, and there exists y such that x and y are adjacent, and there exists z such that x and z are distinct vertices, and y and z are adjacent, but x and z are non-adjacent. And there also exists a vertex x. Maybe it is the same vertex as this x. So when I write this x, I forget about the previous one. So I say that there exists x which is adjacent to z. But this x cannot be equal to this one, because we know that this x doesn't adjacent with z. So they're distinct. So I can write such property about structure on 4 vertices using only 3 variables. So this, what does it say? It says that there exists a path on 4 vertices such that the first vertex and the third vertex are not adjacent. Okay, so I think it is clear. More examples of graph properties which can be represented in first-order language is for example, a property of a graph to be complete. So this is the way how we can represent it. If 2 vertices are distinct, then they're adjacent. Property of a graph to be triangle-free, so there is no triangle. And for example, the property of graph to have diameter 2. If you take any 2 vertices, if they are distinct, then there exists a common neighbor of them. And there exist two vertices that are not adjacent. So the diameter is not 1, but 2. Okay, let me also give some properties that cannot be represented in this language. For example, these 3 properties. Property of a graph to have some fixed chromatic number, say k. Property of a graph to be connected, and the property of a graph to have even number of vertices. So there is a very nice way how we can prove that these properties cannot be represented in first-order language. And this way is combinatorial. and it deals with arithmetic game. So if you want to find the proofs, you can find it using arithmetic game, but I don't have time to give it. Let me now explain how we can represent these properties, not in first-order language, but in second-order language. For example, the property of having even number of vertices. So for doing this, we need quantifiers over predicate variables. So what does it mean? X with this index 2 is a variable for function of two arguments. So it has values 1 and 0. So here I say that there exists a function of two variables with two arguments. And this is also a function of the same function of two variables, and so on. So what I say here? Here I say that I can find such function which divides the set of all vertices into two parts, and the vertices from the first part is for the first argument of the function, and from the second part is for the second argument. So there exists such function that it is 0 for all equal first and second arguments, and such that for every x there exists y such that it is this function equals 1, so it is true, and it is symmetric, and for every other z it is not true. So it means that we have even number of vertices, exactly. Okay, so these sentences are built of the same symbols as in the case of first order logic, but also we have these predicate variables, and we can not only have variables, functions of two arguments, we can have functions of any finite number of arguments, for example, of 5 or of 1. So here everywhere I use an upper index for arity is the number of arguments, for the number of arguments. Okay, so it is easy to see that the property of being connected and the property of having chromatic number equals k also can be represented in this language, and we only need functions of one argument for this. And such sentences are called monadic second order, so we need only unary predicates. So unary predicates means that this predicate has only one argument. And I will denote by, in this way, the set of all finite monadic sentences. And I also need this set. This is the subset of the set of all monadic sentences in which all the quantifiers over monadic variables are in the beginning of the sentence. So we'll have some example to explain it. So for example, the property of a graph to be connected is of course monadic second order, but it's not existential because we have this monadic variable, and before this variable we have not existential but universal quantifier. So what does it say? It says that for every set x, so why I say set? Because what does it mean to consider a function of one argument? It is the same as consider the set, because we have set of vertices for which it equals 1, and there are other vertices for which it equals 0. So I can say that there exists for every set x such that it is not trivial, so there is x inside and there is y outside. So if this set is non-trivial, then there is an edge some problems, yes. It should be exists x here, so that there is an edge between x and complement of x. So exists x, exists y, yeah, such that x of x and negation x of y and x is adjacent to y, I'm sorry. Okay. And the property of graph to have chromatic number 2 can be expressed also in this language, but using existential monadic, because we have only existential quantifiers in the beginning of the formula. Okay. Now let me consider the binomial model of random graph. So I think that most of you know what is it, but I will remind the definition. So we have n vertices, and we consider complete graph on this set, and we remove each edge from the complete graph with probability 1 minus p, or every edge appear in this graph is probability p. So it means, for example, that if we consider a spanning subgraph of the complete graph on this set of vertices with e edges, then the probability of the fact that random graph equals this graph is this: p to the e, 1 minus p to n choose 2 minus e. Okay. So, and my talk is devoted to the probabilities of properties of random graph, and the properties which can be expressed in first order or second order language. So let L be some language, first order or second order. Then I will say that the random graph obeys 0-1 law for this set of sentences. If for every sentence its probability that it's true, this sentence is true for the random graph, converges to 0 to 1. And I will say that the random graph obeys convergence law if all such probabilities converge. So of course from 0-1 law convergence law follows, but if you have convergence laws, then maybe we don't have 0-1 law. Okay, so what do we know about random graph? In 1969, by Glebsky, Kogan, Login, and Talanov, and independently in 1976 by Fagin, it was proved that if p is constant, then the random graph obeys 0-1 law for all first-order sentences. Okay, so what about monadic second order? In 1985, Kaufman and Scheller proved that there is no even convergence law. So there are such sentences for which we don't have any limit. And in 2001, it was proved that there is no even existential monadic second order convergence law. Okay. There were more studies about such questions about random graph. We can consider p like p is function of n. For example, n to some power, alpha is constant and positive. Then in 1988, it was so most of these results were proved by Spencer and Scheller, and one of these results was proved by Lynch. So I give it in one theorem. So if alpha is irrational, then there is 0-1 law for first order sentences. If alpha is rational but from 0 to 1, then there is no even convergence. There is no convergence law. If alpha is greater than 1, and in this interval for such for some m, integer m of course, then there is 0-1 law. If alpha is greater than 2, then there is also 0-1 law. But if alpha equals to 1 plus 1 over m, where m is integer, then there is no 0-1 law, but there is convergence. And if alpha equals 1, there is also convergence law, but there is no 0-1 law. In the case of monadic second order, we have the following results. So if alpha is from 0 to 1, there is no convergence. So we have difference with this case because for irrational alpha we have 0-1 law, and here we don't have convergence. If alpha is in this interval, we again have 0-1 law. If alpha is bigger than 2, then 0-1 law holds, and if alpha is 1 plus 1 over m, like in the previous case, we don't have 0-1 law, but we have convergence law. Okay, so now about the conjecture. So this was the history of the problem. In 1987, Kaufman proved the following thing. So he considered a random uniformly chosen random structure with 4 binary relations. They are not symmetric, so any binary relations. And he proved that there exists a formula for which existential monadic second order convergence law fails, with 4 monadic variables and 9 first order variables. So it has this form. So in the beginning we have 4 monadic variables, and then we have first order part in which we have variable width equals 9. Okay, then in 1998, Libars proved that the same is true for one binary relation, and we can even find a sentence with only two first order variables. And after that, in 2001, he proved that the same is true for symmetric binary relations, so that convergence law doesn't hold for graphs. But in this example, he has much more than 9 first order variables, and he asked, is it true that there is no there is no convergence law, or there is maybe 0,1 law, if we have two first order variables and we consider graphs? And the conjecture is that there is 0,1 law for such sentences, that G of n 1/2 obeys 0,1 law for existential monadic second order sentences with only two first order variables. So what I can prove is the following. So if P is not equal to these two numbers, and we consider sentences with only one monadic and two first order variables, then there is 0,1 law. And for P either 3 minus square root of 5 over 2 or square root of 5 minus 1 over 2, there is no convergence. So there is a sentence, a very simple sentence with one monadic quantifier and two first order variables, for which we have no convergence for such P. So it looks strange because all natural sentences which are so simple and that can be expressed in monadic second order language behaves the same for P equals 1/2 and for other constants P. Okay, on the next slide I will give explanation why it is so. And the second result is that if P is arbitrary constant, then I can prove that there is no convergence, there is sentence with only 3 first order variables without convergence. So the only question we have, is there 0,1 law for 2 variables or not? So for 3 there is no convergence. And I also can construct a sentence with only one monadic variable and without convergence. But in this case, I have much more first order variables. So this result needs very difficult constructions, but the construction for the first result is simple, and I'll give it on this slide. So let P equals 3 minus square root of 5 over 2, and consider the sentence which says that X, that the induced subgraph on the set X is a clique. So for every X, for every Y from X, they are adjacent. And the sentence max, this sentence represents the property that the induced subgraph on the set X is a maximal clique. So what does it mean maximal? That it is a clique and that every vertex outside is not adjacent to at least one vertex of X. Okay, and the last part of my sentence is this. It says that there exists an outside vertex, so the vertex outside X, which is not adjacent to any vertex of X. So it is isolated from all the vertices in X. And then the sentence is this. So for every X, if X is a clique, and there is no isolated vertex which is outside this set, for every such set is maximal clique. So it's very simple to understand this sentence, but it's not so clear why there is no convergence. I will try to explain. So you can see that this sentence is not monotone, but it is convex. So what does it mean? Convex means that it is intersection of increasing and decreasing properties. So its probability, if we change P from 0 to 1, its probability behaves in the following way. So it tends to 0. At some moment it begins tending to 1, and then it again tends to 0. So this there are two moments when this asymptotical behavior changes, say P1 and P2. And so here 0, here the asymptotical probability is 1, and here it is again 0. So I can prove that P1 and P2 are very close to 3 minus square root of 5 over 2. And they're such close to this number that for different integers n is the number of vertices in the graph, we can be outside this interval or inside. So this is why there is no convergence. Well, I want to stop here. Thank you very much for attention.
Thank you very much. Maybe here, any questions or comments? In this case, any activity? Oh, Dmitry, very good. Does it work?
Maybe. Yeah. Can you show again the second theorem? So I didn't understand. So the first theorem says that. So what? So there is without. The second statement says that there is a sentence.
Yeah,
without convergence.
I mean sentence with also one monadic and two first order variables.
What is the difference between the second statement of the second theorem and the first statement of the first?
Yeah, because in the second statement of the second theorem, the number of first order variables is very large. So it's not 2. So here we have one sentence with one monadic and two first order variables, and here we have one sentence with one monadic and many first order variables.
Okay, you didn't mention it. Okay.
More questions or comments? Okay, let us thank Maksim once again.